A neutron decays by emitting beta negative particle. So sometimes they ask you reversed case. If a neutron decays, which particle is released? So it releases beta negative particle. So beta negative has -1 as charge and approximately 0, which we write 0 as mass. Anti-neutrino is released, which has no mass and no charge. And neutron decays by emitting beta negative particle, and the neutron is decayed into a proton. Proton 1 here, 0 at the top. So this is what we get. Now if you compare the left side and the right side, the atomic number on the left side and the total atomic number on the right side should be same. And matter of fact, where we study this thing, the neutron decays by emitting a beta negative particle. We did this one exactly over here. Look, in the lesson, neutron decays into proton. Where is that one gone? State the name of the particle represented by the symbol. Okay, the follow-up question was this one. Anti-neutrino. State the name of the class of particles that beta negative and anti-neutrino belong. They're not made up of any quarks, so these are known as leptons. Protons and neutrons are made up of quarks. State the quark structure of the neutron. Neutron up, down, down. So proton is up, up, down. Neutron is down, down, up. The change to the quark structure when the neutron decays. So when the neutron decays, one of the down quark is changed into up quark. Okay, let's take a look at the next one. Give one example of a hadron. Hadron is something which is made up of 3 quarks, for example proton. A lepton, something which cannot be further divided, for example electron. Describe in terms of simple quark model a proton. Up, up, down. Neutron. Down, down, up. Beta particles may be emitted during the decay of unstable nucleus. Okay, so neutron is converted into proton, beta negative is released, and anti-neutrino. Anti-neutrino is a curved V. You write normal V, they deduct the mark. It should be curved V followed by a bar at the top, which is anti-neutrino. So that is the equation. Since they have written in the full word, the word equation instead of symbol, so I'll write proton. Beta negative, which is the same thing as electron, they are fast moving electron. And antineutrino. So this is the word equation. So antineutrino, whenever you have a neutron converted into proton, in which beta negative is released. Change, state the change in quark composition of the particles during this. So neutron to proton. Neutron to proton. So means down, down, up. One of the down quark would be changed into up quark. So if one of the down is changed into up, so you're left with one down and two up, which becomes a proton. State the name of the class group to which each of the following belongs. Starting from the electron, which is a fundamental one which cannot be further divided. So this one belongs to leptons. Neutrons can be divided into 3 quarks. So this is baryons. Neutrino, leptons. Antineutrino, leptons. Protons can also be divided into quarks. So baryons. Or you can also say hadrons, because they consist of quarks. Anything which consists of quarks is hadron. But if that thing consists of 3 quarks, it is baryon. So baryons are basically a subtype or a subset of hadrons. So either of these two could have been written. So you could also say hadrons, because anything that contains quarks, irrespective of the number of quarks, is hadron. Proton may decay into neutron together with 2 other particles. Complete the equation. Proton into neutron with the beta positive. For proton to neutron, it is beta positive. Neutrino is released, 0 0. This one is plus 1 0, and neutron is 0 charge and 1 relative mass. Then you can see, if you add all of these 0 plus 1, you get 1. On the left side also you have 1. Write the equation for this decay in terms of quark composition. Okay, sure. So up, down, converted into up, down, down. So one of the up was converted into down. State the name of the force responsible for this. Weak nuclear force. Okay, then we have the next one. Distinguish between alpha particle and beta particle for 3 marks. So you can talk about their mass, you can talk about their charge, you can talk about their number of protons and number of neutrons, stuff like this. So alpha particles, and on the other side you have beta positive particle. So alpha particle, they have two protons, two neutrons. Beta positive particles are basically the fast moving positrons or the anti-electrons or positive electron, we also call it. Alpha particles have a relative charge of plus 2e. Beta particles have a relative charge of plus 1e. Alpha particles have a relative mass of 4u. Beta particles have a relative mass of 1 over 1840 u. So just a fraction, like approximately 2000 times smaller in mass. State the equation that shows the decay of the particle of a nucleus that results in beta positive emission. It means proton into neutron. For which one? For beta positive emission, it is proton into neutron. What other particles are released? Proton into neutron is beta positive plus neutrino. So 1 0, 1 0 1 1 0 0 0, and you can see the left side and the right side, these are balanced. State the quark composition of proton. Up, up, down. Neutron, down, down, up. Use a quark model to explain the charge on the proton. So the charge on the proton, quark containing the proton are up, up and down. Charge on up is 2 by 3e. Charge on the second up also 2 by 3e. Charge on the down quark is minus 1 over 3e. If you add all of them, that becomes 3 by 3e with the positive sign, which is equivalent to 1e. So that is the charge on the proton. Then we have the next one. State one difference between hadron and lepton. Hadron consists of quarks, but leptons are fundamental particles. They cannot be further divided. So hadrons can be divided into quarks. Leptons, for example, electron is a lepton. Leptons cannot be further divided. State the quark composition of a proton and neutron. Proton is up, up, down. It should have been memorized by now. Neutron is down, down, up, or up, down, down. Determine the quark composition of alpha particles. So alpha particles contain 2 protons and 2 neutrons. So a single proton consists of 2 quarks, consists of 3 quarks, up, up, down. A single neutron consists of 3 quarks, down, down, up. So what do we have in total? So in total we have 2, 4, 6. 6 up, 2, 4, 6. 6 down. Altogether we have 6 up and 6 down quarks. Then we have the next one. The results of alpha scattering experiment provides the evidence for the structure of the atom. The result 1. But we need to find the conclusion, what may be inferred from result 1. So what is the conclusion made from this statement? So you cannot write the simple generalized conclusions from alpha scattering experiment. What is the conclusion that you make From this very statement, the vast majority of alpha particles pass through the metal foil or are deviated by small angle. So most of them either pass through as it is or are slightly deviated. So atom is mostly free space or empty space. Result 2. A very small minority of alpha particles are scattered through angles greater than 90. So a few uh, amount of the particles were deviated at large angles, which means the mass of the atom is concentrated in a very small nucleus which is positively charged. Or you can combine these two to write a single statement. For example, you can phrase it in a better way. Most of the mass of the atom is concentrated in a tiny region carrying a positive charge, which is nucleus. State one difference between state one difference between hadron and lepton. So hadron contains quarks. They can be divided into quarks. Leptons, these cannot be divided into quarks because these are fundamental particles. Proton into neutron, beta positive and neutrino, 0 0 and 1 0. If we have neutron into proton, then beta negative is released. State the name of the force that gives rise to this decay. Like we studied it already, it's always the weak nuclear force. State three quantities that are conserved in the decay. Okay, so one of them is momentum, one of them is mass energy. You don't say energy because we studied a topic which we call mass energy conversion. So energy can be converted into mass can be converted into energy. So mass energy remains conserved. Mass energy, momentum, and you can say, for example, the lepton, the charge or the proton number or the nucleon number, because at the bottom the number of proton on the left side, number of protons on the right side is 1. At the top, the atomic number, the mass number on the left side is 1, the mass number on the right side is 1. So atomic number or charge or mass number or atomic mass, you can write either of those. Charge, nucleon number, proton number, any of these can be written, but this is a very important one because many of the students are tempted to say energy. No, mass energy. Use quark composition of a proton to show that it has charge plus E. Up, up, down. Up is 2 by 3e, relative charge. The second up also 2 by 3e, the relative charge. The third down is 1 by 3e, the relative charge. You combine all of them. Denominator is same. No need to take the LCM. 2 plus 2, 4. 4 minus 1, 3. E as it is. 3 by 3 cancelled out. You're left with plus 1e, which can also be written as, without the coefficient 1, simply e. So this is everything that we have done